Alright, hello everyone. Hope you guys are doing good. So today I'm going to be discussing the solutions to Codeforces Round 786. This was the Division 3 round which was held yesterday. There were 7 problems and I'm going to be discussing all of these problems today. Before that, let's just talk about the round. I think this round was a little bit on the easier side as compared to a typical Division 3 round. But nevertheless, I found this round to be, really ideal. The difficulty rise in the problems was the way it should be, and also the actual difficulty of the problems was also a bit ideal because there were no problems which required a lot of special techniques, right? If you leave aside the last problem maybe, then the first 6 problems didn't require anything very special, and any beginner could solve the first 3 or 4 problems very easily. So in that aspect, I think this round was very ideal, right? So yeah, that's my take on the round. So now let's start with the solutions. I'll be discussing all the problems. So we'll just quickly go over the first 2 problems because they are really easy, and then we'll start with the third problem. So let's see the first problem. So here we have been provided with two integers x and y, and we want to choose two strictly positive integers a and b, and then apply the following operation to x exactly a times. We have to replace x with b times x, and we want to find two positive integers a and b such that x becomes equal to y after this process, and if there are multiple possible pairs, you can choose any one of them. So basically we just need to tell if there is a pair a comma b such that if we replace x with b times x exactly a times, then we will get a number which is equal to y. Okay. And if there are no possible pairs, we need to output a 0 comma 0, otherwise we need to output the values of a comma b, and the answer is the solution is very simple. After one operation, our x becomes bx. After two operations, our x becomes b into bx, which is b square times x. Similarly, after we do exactly a operations, x will become b raised to the power a times x, and we want this number to be equal to y. So obviously for a pair to exist, y should be divisible by x, right? So first thing is that y should be divisible by x, and the second thing is that we need to find two numbers a and b. So we need to find a pair a comma b such that b raised to the power a is equal to y upon x. And a very simple solution for that is to take a is equals to 1 and b is equals to y upon x. Then we'll just have y upon x raised to the power 1, which is obviously equals to y upon x. The only condition that needs to be satisfied is that y upon x should be an integer, and this will be enough for our solution because according to the constraints of the problem, x and y are really small and the values of a and b that we can output are really large. So we can be sure that y by x will always be in this limit of 1 to 10 to the 9, and 1 is obviously within the limit, so that is not a problem for us. So we can simply output 1 and y by x if y by x is an integer, otherwise we can just output 0 0, and that's it. So the code again is really simple. All we have to do is check if y modulo x is equal to 0 or not. If that is the case, then the answer is going to be a is equal to 1 and b is equals to y upon x. So yeah, that completes the solution to the first problem. Now let's quickly move to the second problem. Again, this is a very simple problem, even easier than the first problem, I would say. So here we have the Berland language, which consists of exactly 2-letter words. So, and also the first letter can never be equal to the second letter. So any combination of two characters which are different from each other is a valid word in the Berland dictionary. And in the problem, basically we'll be provided with a word that is a 2-character word, and we just have to output the position of that word in the dictionary. And in a dictionary, the words are numbered according to the standard definition, so they are numbered lexicographically. So yeah, that's how the numbers are there in the dictionary, and we just need to tell the position of that particular word in the dictionary. Again, the solution is really easy. So basically what we can do is we can pre-compute the position of all the words, since the number of words is really small. So the number of words is basically for the first character we have 26 choices, and again for the second character we have 26 choices, and we have 26 words which are which contain the same character twice, so we will subtract 26. So the number of words basically is 26 into 25, which is equal to 650. And so this is a very small number, so what we can do is we can pre-compute the position of each and every word. And the way we can do this is, first of all, obviously the character which will be at the first position would be AB, character at the second position would be AC, then we'll have AD, AE up till AZ, and then we'll have BA, then we'll have BC up till BZ. Similarly, then we'll have CA, CB, CD up till CZ, and so on and so forth. So we can just have a nested for loop, and we can just create the current word and then assign a position to it, and we can do that for each and every word. Let's just have a look at the code. That will make things a lot more easier. So even before reading the test cases, what we are doing is we are having this map which is from a string to an integer, and it maps all the strings which are there in the Berlin dictionary to their positions. And for doing that, what I'm doing is I am having two nested loops from 0 to 25, and if I is equal to j, I simply continue, because we can't have a word which has the same character twice. And then I'm just constructing the string which has the ith character as its first letter and the jth character as its second letter, and I am saying that the position of that particular string is the current position on which I am at, and then I increment the current index. And that's it. Once I'm done, I'll have the positions of all the strings, and then I'll just read in the input string and output its position, which I have already pre-computed. Okay, so yeah, that completes the solution to problem B. Again, a really easy problem. Now let's move to the next problem, problem C. So in this problem, we have been provided with two strings S and T. The condition is that the string S only contains the letter A several times, and the string T can contain anything, right? And in one move, what we can do is we can replace any letter in any of the letters A in the string S, and we can replace it with the entire string T. Okay, so basically what we do is we remove an A from S, and in place of that A we put the entire string T, and that's it. That is an operation, and we are allowed to perform an arbitrary number of operations. And finally what we need to tell is we need to tell the total number of different strings S that we can get, right? So yeah, that's the problem. So we are allowed to do this operation as many times as we want, and we just want to tell what is the total number of strings S that can be, and what is the total number of strings that can be there in place of S after doing that operation. And yeah, that's the problem. So again, this is not a very difficult problem. This is just some casework that we need to analyze. So let's just try to make a few cases and try to analyze the solution. So there are basically three cases in this problem. So let's have a look at the first case. So the first case is a trivial case, and that case is when the string T is equals to nothing but A. So in this case, what exactly happens is that we are basically replacing an A with an A. If you notice carefully, what we are allowed to do is we are allowed to remove an A from the string S, and then we have to insert the entire string T there. But if the string T itself is equal to A, then we are basically removing an A and inserting an A. So the string S remains undisturbed. The string S is never changed, and hence the answer is always equal to 1, which is the original string S that we have, and we can never change it, right? So this is the first trivial case when the string T is equal to A. So now let's look at the second case. So the second case is that T is not equal to A, obviously. So T is not equal to A, but T contains some A's. So yeah, this is the second case. So that means the frequency of A in T is greater than 0. And in this case, what I claim is that the answer will be infinity. So they have also said that if the answer is infinity, then we have to output -1. This is a detail of this problem. So I claim that if the string T is not equal to A, but it contains some non-zero amount of A's, then the answer will always be infinity. And the way we can prove it is that in every operation, what is happening is, so in every operation, first we remove an A, and then we insert the string T. So let's have a look at the frequency of A in the string S. So let's look at the frequency of A's in S. So what happens is, first of all, the frequency decreases by 1 because we remove an A, and then it increases. So let's say that it contains some A's, and let's say that this value is X. So what happens to the frequency is, let's say that the initial frequency was F, then the final frequency will be F minus 1 plus X, where X is the amount of A's in the string T, right? So if the value X is greater than 0, obviously this frequency is a non-decreasing function, right? So if X is greater than 0, then F will be a non-decreasing function. And the thing to notice here is that we can do this operation as long as there is at least one A in S, right? And if there is always an A in S, then we can just infinitely keep doing this operation, right? So another thing to notice is that we can do an operation as long as there is an A in S. And since the number of A's was initially non-zero and it is a non-decreasing function, it will never become 0, right? So if F is non-decreasing, then F will never become 0. Hence the process will continue indefinitely. Right? So this is how we can say that if the string T contains an A, then for sure the answer will be infinity, because we can just keep getting new and new strings by doing this process again and again. So yeah. So the another thing to note here is that every time we do an operation, we get a brand new string. Obviously, because we are replacing an A with a string with length at least 1. So obviously we will get a brand new string every time. That is a string which we have never got before. So it will be a unique string that we will get every time. So now let's look at case 3. And case 3 is T doesn't contain A's, any A's. And so I will write down this observation that I have made before, which is that every time we do an operation, we get a unique brand new string. Okay. And also the number of operations that we do is obviously equal to the number of A's in the string S, because in every operation the number of A's here is decreasing by 1, since X here is equal to 0. So we can say that F turns to F minus 1, then F minus 2, and eventually it reaches 0. So since the number of A's decreases by 1 every time, the total number of operations that we can do is equal to the frequency of A's in S. And the frequency of A is nothing but the size of S, because S contains only and only A's. So the total number of operations, the maximum number of operations that we can do is the size of S. And another thing that we have already noted is that each operation that we decide to do gives us a totally brand new string. So we can do any number of operations from 0 to size of S. Let's say that size of S is n. So we can do any number of operations from 0 to n, and every operation that we do produces a unique string. So that means we can have any subset of operations from size 0 to size n. And the total number of subsets of a set of size n is equal to nothing but 2 raised to the power n. Okay. So we can either do one operation, we can either do two operations. So if we decide to do two operations, then there are nc2 ways. If we decide to do three operations, then there are nc3 ways, right? So the total number of ways are, if we decide to do 0 operations, there are these many ways. Then there are these many ways if we decide to do one operation. Then if we decide to do two operations, we have these many ways. Similarly, this will sum up to ncn. And it is a well-known property that the total sum of these values is nothing but 2 raised to the power n. And this is going to be our answer. Right? So these are the three cases that we had to look in this problem. And yeah, so this basically completes the solution. If there is if t is equals to a, then answer will be 1. If t contains a, then the answer will be infinity. And if t doesn't contain any a, then the answer will be 2 raised to the power n, where n is the size of a, n is the size of s. So yeah, that's it. Let's just have a quick look at the code. So there is nothing special here. If s2 is equal to a, then answer is 1. Sorry. If the count of a in S2 is non-zero, then answer will be -1, which is infinity. And thirdly, the answer will be 2 raised to the power count, where count is the size of S. That's it. Okay, so this completes the solution to problem C. Now let's move on to problem D. So I kind of enjoyed solving problem D. So I think it is a very ideal problem D for a division 3 round. It uses some observations. You have to use pen and paper to write down what exactly how exactly things will look like, and the final solution comes out to be very elegant. So I really enjoyed this problem. Let's have a look at the problem. So we have 3 arrays with us, A, B and C. Initially, array A contains n elements and arrays B and C are empty. And we do 2 steps. In the first step, we build the array B, and in the second step, we build the array C. So let's see how things are going on. So in the first step, while the array A is not empty, what we do is we take the last element from A and we move it to the middle of B. And obviously, if the array B, if the current length of B is odd, then the middle position is not defined. So we can choose to place the element either to the left of the middle element or to the right of the middle element. And if the number of elements in B is currently even, then we have exactly one middle position. So we just have to place the last element from A there. So by doing this, we can completely build the array B. And there will be various choices for the positions of a lot of elements in B. But finally, we will build the array B. And once we have built B, then we will try to build C using B in step 2. So in step 2, what happens is while the array B is not empty, what we do is we take the middle element from B and we move it to the end of C. Now obviously, again, if the length of B is currently even, then there is no one middle element, there are 2 middle elements. So we can choose to take any of the 2 middle elements. That is completely our choice. So you can see that there are a lot of choices involved here. There are a lot of choices in the first steps and there are a lot of choices in the second step. So I hope both of the steps are clear enough. So the problem asks us, is it possible to have an array C starting from an array A such that the final array C is sorted in non-decreasing order? So yeah, that's the problem. So we have to make these choices in step 1 and step 2 in such a way that the final array C is sorted in non-decreasing order. We just have to output yes or no whether or not it's possible to have such a situation. Okay. So let's try to make some observations and see how things are looking like. So we have this array A. We have A as A1, then A2, then A3, up and so on up till AN, right? Now let's try to build B. Okay, we will try to build B. Let's say that the length of A is 7. So let's say n is equals to 7. So how is B going to look like? So let's try to find out the position of the first element of B. So notice in the first step, what we are doing is we are basically taking the last element of A and we are moving it to the middle of the array B. So and we are doing this from right to left. Okay, so first we take an, then we take an minus 1, and finally we will take a1. So let's see where will a1 go. Okay, so when we are inserting a1 into B, we know that B already contains 6 elements, right? Okay, so we already know this is the situation. And let's say that the length is 7. Okay, and we know that B already contains 6 elements, and there is exactly one middle position because the length is even, and that will be this position here between the third and the fourth element. So we will just insert a1 here. Okay, so what we do is we simply insert a1 here. So a1 comes here. Okay, so we know for sure that in the array B, the element a1 will be at the 4th position. Okay, now let's try to find out the position of a2. Okay, so then what happens is that So now when we are trying to insert A2 in B, we have already inserted elements from A3 to A7. So the length will be 5. Okay. So it will look something like this. So now since the length is 5, we can see that if array B has odd length, then there are two choices that we have. We can either insert the element to the left or to the right of the middle element. So the middle element, as we can see here, is equal to this third element. So we can either insert it here and then it will look something like this. So if we insert it here at the third position, then here will be our second element, right? And the second choice that we have is to insert it at the insert it to the right of the third element, and that is at the fourth position. So this is the third element and this is to the right of the third element, so we have this position, fourth position. So this is how it's going to look like. So these are the two choices that we have. Okay. Now what happens is that we have this one also, right? So these are the two choices that we had for to put A2, and now when we will put A1, we know that we are putting A1 at the fourth position, right? So in the first choice, A1 will come here, and in the second choice, A1 will come here. So A1 will come in between these two elements. So it will look something like this. So A1 will come here. Okay. So these are the two choices that we have. So what we notice from here is that either we will have a situation, or either 2 will come to the left of 1 or 2 will come to the right of 1. Okay. So these are the two situations that we will have. Yeah. Okay. So now what happens is that we will look at the position of the third element, obviously. So now when we look at the position of the third element, so the third element, obviously, now the third element will have just one choice and it will come here, either here or here. Okay. So what we notice here is that if n is odd, what is happening is that the position of A1 is defined and it will be the middle position. Now we can have a situation like this. So let's say A1 is here and A2 can either be to the left. In that case, A3 will be to the right of A1. I'm sorry. Yeah. A1 will be here, and either we can have a situation like this or we can have a situation like this where A3 will be to the left or A2 will be to the right. And we can continue this process so on and so forth. In the first choice, we again have two choices. Either we can have A4 to the left and A5 to the right, or we can have A5 to the left and A4 to the right, something like this. And this process can just keep going on forever and ever, right? So this is basically how the array B is going to look like. Okay. Now we will see how the array C is going to look like. That is because that is the final array in which we are interested in, right? Okay. Yeah. So now let's see how this array is going to look like. So let's look at step 2. Now in step 2, what is happening is that while B is not empty, we take the middle element from B and we move it to the end of the array C. Okay. And that means first we take an element from the middle of C and we put it to the end of first we take an element from the middle of B, put it to the end of C. Then we take a middle element from B, put it to the right of the previous element, and so on and so forth. That means the first element that we will take out from B will eventually become C1, right? And that element is going to be the middle element, right? And the middle element, as we already know, is going to be A1. So the first element of C is going to be A1 for sure. Okay. Now what happens is that now we will take the middle element again, but now there are two choices for the middle element. Either we can take this 2 or we can take this 3, because both of them are viable candidates for being the middle element. So now we have two choices. First of all, we can get an A2 here and an A3 here, or what we can get is we can get an A1, then an A3, then an A2. Similarly, for the next two elements, we have two choices. We can either get A4, A5, or we can get A5, A4. And similarly, next we can get either A6, A7 or A7, A6. And that is how the process will go on. So the general structure of C will look something like this. A1, then we will have A2 slash A3. Then again we will have A2 slash A3. So it is our choice to arrange A2 and A3 in any way that we want. Then we will get A4 slash A5. Then we will again get A4 slash A5 in any way that we want. And this is how the process will go on. Okay. And obviously if n is even, then this A1 will not be there. Then we will have, so if n is even, then we will have something like this. So from the first index itself, we won't be having any choices. So we will have either A1 or A2 here. And in the second position, again, we will have A1 and A2. Then we will have A3, A4. I mean, you basically get the idea, right? So this is how things will look like. The only difference between even and an odd n is that for odd n, the first element of C is fixed to be equal to A1. And then we have choices starting from the second element. But if n is even, we will have choices starting from the first element itself. Now, what we want is, we want to sort array C. Now our best shot at getting the array C sorted is to always keep the minimum element first and then the maximum element, right? So we will keep the minimum element first and then the maximum element. Out of the two consecutive elements, we will always keep the minimum first, because if we keep the maximum first, then we simply encounter an inversion, and we don't want any inversions in the sorted array, because that makes the array unsorted then and there, and that is not what we want. So the best shot at getting the array C sorted is to first keep the minimum element, then keep the maximum element. So we just know how to make these choices. These choices are made in such a way that to the left we keep the minimum and to the right we keep the maximum. So the way we can check this is, we just build the array C completely by keeping the minimum to the left and the maximum to the right, and finally we will just check if C is sorted or not. If C is sorted, then the answer will be yes, otherwise the answer will be no. I hope I am making sense. So this is the complete solution. Let's just have a look at the code. So if n is odd, then C1 is obviously equal to A1. And then what we do is, if n is odd, we start with 2, otherwise we start with 1, and we increment our I by 2 every time. So we have AI and AI plus 1. So Ci is going to be minimum of AI plus 1, and Ci plus 1 is going to be maximum of AI plus 1. So finally we will have the entire array C built with us. So we'll just check if C is sorted or not using the inbuilt is sorted function in C++ STL. And if that is the case, then answer will be yes, otherwise our answer is going to be no. So I hope I was I hope I was able to make things clear. So if you didn't get this part, why this is happening, then you can use a pen and paper and try to visualize the entire step 2 which is going on, and it will come to you very easily. Okay. Yeah. So yeah, this completes the solution to problem D. Now we can move on to the next problem, which is problem E. And there is a very interesting thing which is going on with problem E, and we'll see everything about it. Okay, so the problem E, as you can see, had only around 550 solves during the contest, but actually when the contest ended, there were around 1300 to 1500 solves to this problem, and that means more than 60 to 70% solutions of problem E have got hacked, and that is something which is very, very rare. Like, almost all of the solutions got hacked. There are rarely a few solutions which didn't get hacked, including mine. So that is great. So let's see what the problem is, and let's analyze what cases the most of the people missed here. Okay, so in this problem, basically what is happening is, we have an array A of n elements, and our goal is to make at least 2 of these elements equal to 0. And in one step, what we can do is, we can choose an element and we can try to hit that element. And when we hit the ith element, what happens is that we cause a damage of 2 to the ith element, and then we cause a damage of 1 to both of its adjacent elements if they exist. And that's all that's going on here. Okay, we decide to shoot the ith element, and which element we decide to choose is totally our choice. And we decide to shoot that element, and that element decreases by 2, and the elements which are adjacent to it, they decrease by 1. And this is how the process is going on. Our goal is to calculate the minimum number of shots that we need to make such that we can get at least two elements to be equal to 0. Okay, so that is the problem. So let's try to make some cases and then let's analyze how we can solve this problem. So in problems like this, where we have to make at least 2 or at least 3 of some things to be equal to 0 or something like that, the best way to approach these problems is to iterate on which two of these will we be making 0. So what we'll do is we will think about which two elements will we be making 0. And we'll try to make cases about which two elements we'll be making 0, and this is how we are going to work. So let's look at the first case. So let me first write down all the three cases which are there. Okay. So the first case is that these two elements, so the number of elements between them, so let's say these two elements are I and j. Okay. So we are making the ith and the jth element to be equal to 0, and the first case is that the number of elements in between I and j is greater than 1, strictly greater than 1. Is strictly greater than 1. The number of elements between I and j is nothing but j minus I minus 1. It is greater than 1, implies that j minus I is strictly greater than 2. Okay. The second case that we are talking about is that both I and j have exactly one element between them. So they have exactly one element between them, and it's funny that this case too is the case that people missed, and this is the reason why people have been getting hacked a lot in this problem. So a lot of people missed case 2. So exactly one element between them, that means j is equals to I plus 2. And case 3 is that both I and j are adjacent. Right. So these are the two possibilities. These are the three cases that we have. Let's try to analyze all these three cases and let's try to find out the best answer for all the three cases, and then we'll just simply take the minimum. Okay. So according to the first case, the number of elements between I and j is strictly greater than 1, which means that if this is the ith element, then there are some elements, let's say 3 elements in between, and then this is the jth element. So if we look at any shot which decreases the ith element, it is not possible that that particular shot affects the jth element. Why? Because any shot which affects the ith element will either be at the ith element or be at the I plus 1th element or be at the I minus 1th element, and none of these three shots affect the jth element at all, and the same is the case with the jth element, right? So in this situation, obviously it's best to keep attacking I until it becomes 0 and keep attacking j until it becomes 0. And obviously if we keep attacking I, then the number of operations it will take is the ceiling of ai by 2, and then if we keep attacking j, the number of operations it will take will be aj by 2. And so the sum will be ai ceiling of ai by 2 and plus ceiling of aj by 2, and we have to take the minimum over all the values. So since any shot which affects I can never affect j, the best strategy would be to keep hitting I and then keep hitting j until both become 0. So the number of operations that it will take, so the final value that we'll get here is the minimum over all ij of ceiling of ai by 2, which is ai plus 1 integer division by 2 plus bj plus aj plus 1 upon 2. Okay. And obviously if we take this minimum over all pairs, the best value that we will get will be for the two minimum elements, right? So let's say we sort the array A. So after sorting, we will simply take a1 plus 1 upon 2 plus a2 plus 1 upon 2, and that will be our value that we will get for case 1. Now one might argue that it is possible that the minimum and the second minimum element are not satisfying this condition of I and j being strictly greater the number of elements between I and j being strictly greater than 1. It is possible that they have exactly one element, or it is also possible that they might be adjacent. But what I'm claiming is that if it is the case that they are adjacent or they have at least one element, then I am considering that in case 2 and 3, right? And that will give me a strictly lower answer. So it is not a problem for me. So the lowest answer that I can get for case 1 is the minimum element of A plus 1 upon 2 plus the second minimum element of A plus 1 upon 2. So this is the first value that I'm getting. Now let's look at case 2. So this is the most interesting case which a lot of people actually missed. So this case says that exactly one element is there between I and j. So this is the ith element, this is the one element between them, and this is the jth element. Okay. Now if we look at any short which affects the ith element, it can either be at I minus 1 or at I plus 1. Okay. So if that short is at I, then it will affect then it will decrease I by 2, and it won't decrease j at all. Okay. So let's see. So if we hit at I, what happens is that AI decreases by 2, AI minus equals to 2, AJ unaffected, right? And the second choice, I mean, obviously it doesn't make any sense to hit at I minus 1, because it is better to either hit at I or at I plus 1. So let's say we hit at I plus 1. In this case, what happens is that AI minus minus and AJ minus minus. Okay. So in the first case, we get a total benefit of 2. Similarly, in the second case, we get a total benefit of 2. And the third case is that we hit at j. So if we hit at j, then what happens is that AI remains the same and AJ decreases by 2. Again, the total benefit is of 2. And so what that means is that we can always perform the first case, but we cannot perform the first, like we won't be getting a benefit of 2 from the first type of hit at x equals to I, because AI will be less than equals to 2. So like if AI is less than 2, that means if AI is equal to 1, then we will get a benefit of 1, otherwise we will get a benefit of 2. Okay. Similarly, we can try to perform the third hit every time, but we will get a benefit of 1 if AJ is equals to 1, and we'll get a benefit of 2 otherwise. But the good thing that we have is that we can always have this hit of I plus 1. And once we hit at I plus 1, what happens is that we will always get a benefit of 2. It doesn't matter whether AI is equals to 1 or AJ is equals to 1. We will always get a benefit of 2. So then what we get here is that we can keep hitting at I until it becomes 0 or 1. So until it becomes less than 2. Same for j. And then if any one of AI and AJ is greater than 0, then we can hit I plus 1 to make both equals to 0, right? So this is the optimal strategy, because at each time we are making sure that we get a benefit of 2, and there is only this one last move where we can get a benefit of 1 instead of 2, and we cannot do better than this, right? So this is the optimal strategy of hitting. And the number of operations that it requires is that, first of all, I will have AI by 2 operations, and this is not ceiling division, this is floor division. So AI by 2, because I just want to make it smaller than 2. So the number of operations will be AI by 2, and then it will be AJ by 2, and plus there will be one extra operation only if either AI is odd or AJ is odd. So plus if 1 if either AI or AJ is odd. Okay. If both of them are even, then in doing AI by 2 plus AJ by 2 operations, both of them become equal to 0. So we don't have to hit at I plus 1 for the last time. And if both of them are even, we basically get to this first case where we are just simply hitting the first element and then we are hitting the second element and then we are done. But now we are talking about the second case. So if both of them are even, we don't even need to consider the second case. We will consider this only if both of them are odd, and the number of operations will be ai by 2 plus aj by 2 plus 1. So what we can do is we can iterate for all i's from 1 to n minus 2 basically, and then we can find out this value, which is ai by 2 plus ai plus 2 by 2 plus 1 if either ai or aj is odd. Okay. So yeah, this completes the second case. And now let's look at the third case where both I and j are adjacent. This is again a really simple case. So here we have the ith element, here we have the jth element. Now obviously at each time we will either hit the ith element or we will hit the jth element. But which one do we hit? Well, obviously we will hit the one which has the greater value currently. So we will hit the element which is currently greater. Now this is a very standard greedy problem, that we have a lot of elements, we are decreasing some of them by 1, and we want to minimize the number of moves. So we obviously always take the maximum element and then we decrease it, right? So here again we will hit the maximum element and we will try to decrease the maximum of these two by 2 and the minimum of these two by 1, because it doesn't really make any sense to decrease the maximum by 1 and the minimum by 2, because the minimum is already smaller and our goal is to make the greater element smaller. Okay, so we will hit the element which is currently greater. So then there are again two sub cases. Let's just assume that ai is greater than ai plus 1. ai is greater than or equal to ai plus 1 for simplicity. If that's not the case, then we can just reverse them. So the first sub case here is that ai is greater than or equals to 2 times ai plus 1. In this case, what happens is that in every operation, ai remains greater than ai plus 1. So ai is always greater than ai plus 1. This is very easy to prove, because after x operations, the value of ai will be ai minus 2x, and the value of ai plus 1 will be ai plus 1 minus x. And since we know that ai is greater than or equals to 2 times ai plus 1, we will be sure that the value of ai is greater than or equals to the value of ai plus 1 every time. Okay. So if this is the case, what happens is that we will always use ai. So we will always hit on ai, and the number of moves, so the number of moves required will be ai plus 1 upon 2. And we will always try to hit ai, and we can be sure that once ai becomes equal to 0, then ai plus 1 would have already become 0, because ai is greater than or equals to 2 times ai plus 1. So these are the number of moves. I hope this was easy to understand. Now let's look at the second sub case, which is that ai is less than 2 times ai plus 1. And in this case, what happens is that every time we will choose the minimum element, every time we will choose the maximum element, and we will try to decrease it by 2, and we can be sure that the other element will be non-zero here, and that will be decreased by 1. So in total, we are getting a benefit of 2. We are getting a benefit of 3 every time. And if we are getting a benefit of 3 every time, then the total number of operations it will take is obviously equals to ceiling of ai plus ai plus 1 by 3. And if we are doing ceiling, then we can just add a 2 here. So if you are if you are facing any difficulties in understanding why exactly we are getting a benefit of 3 every time, then you can try and take an example. Let's say we take an example of 5,7. Okay. So what happens is that after one move it will become 4,5. Then after another move it will become 3,3. Then after another move it will become 2,1. And then we see that the maximum element has changed from ai plus 1 to ai. So now we'll hit at ai, and then it becomes 0,0. So at every time we had a benefit of 3. You can try to take some bigger examples, and you will realize that this will always be the case. And so the benefit that we will get here is ai plus 1 plus 2 upon 3. So now these are all the cases that we had to take. And once we take all these 3 cases, we just have to find the minimum of the 3 values that we'll be getting. And that is going to be our answer. So yeah, that's the entire solution. I hope I was able to explain it well enough, and I hope I was able to explain why people were getting hacked. People were getting hacked because they didn't handle the second case properly. Okay, so now let's have a look at the code. So the code is pretty simple. The first case, the answer that we'll be getting is the minimum element plus maximum element. Obviously their ceilings by 2. uh, okay, so that's one thing. This array B is equal to the array A sorted. So B1 is the minimum element and B2 is the second minimum element. Now we look at case 2. So in case 2 we are iterating for from 2 to n minus 1. So that means we are looking at I minus 1 and I plus 1 as the two elements which are getting destroyed. What we do is if either of them is odd, so this line is basically not necessary, but still we can have it. So what happens is that if either of them is odd, then we will minimize our answer with ai minus 1 by 2 plus ai plus 1 by 2 plus 1. As you can see, this is the exact expression that I have written here. Okay, and this is the second case done. Now we'll look at the third case. Now we will look at every adjacent pair. We will look at their minimum element and their maximum element. So if the maximum element is greater than twice the minimum element, then the candidate answer will be the maximum element plus 1 upon 2. Otherwise the candidate answer will be the minimum element plus maximum element plus 2 upon 3. Okay, so yeah, these are all the three cases that we had to consider. So I hope you guys were able to understand, and that is it for problem E. Now let's move on to problem F, which is relatively a simple problem. So let's see what this problem is saying. So basically what we have is we have a grid which contains of dots and stars. So there are a few dots and there are a few stars. We have an n cross m grid where both n and m are up to 1000, and we have q queries. In every query what happens is that we either add a star at a particular position, or we either remove a star from a particular position, right? So in a query we'll be provided with a row and a column, and we'll be asked to change the state of that particular cell. If it contains an icon, if it contains a star, we have to remove a star. Otherwise if it contains a dot, we have to add a star there. Okay, so that is what happens in every query. And now comes the interesting part. So what we have to answer is, so basically we don't like the board like this. What we want, the way we want the board to look like is, we want to try to move all the stars to the left as much as possible. So essentially our target is to occupy some prefix of full columns, and then we will have one column, and then we will have one row, and we will have some prefix of that row also filled, right? So we have to occupy some prefix of full columns and possibly some prefix of the next column. Okay, so what they want to say is that if we have an n cross m grid, then we and there are like k stars here, then we fill the first few columns with stars, and then we fill the first few elements of the next column by stars, such that each and every star becomes basically a prefix of the entire grid, right? So I hope this is making some sense. So let me try to explain it diagrammatically also. So what basically they want to do here is, let's say we have a grid and there are a few stars in this grid. So the final state of the grid that they want is, let's say there are 10 stars in this grid. So the final state of the grid that they want is that every star should be occupying. So we will have a prefix of entirely filled columns, and then we will have one column whose some prefix from above is filled. So this is the final state of the grid that we want if there are 10 stars. So there are these two completely filled columns, and then this next column has some prefix filled. Okay, and it doesn't matter where the stars initially are, finally they should be in this position. And the operation that we are allowed to do here is that we can, in one operation, pick a star and move it anywhere that we want. Okay, so yeah, that's the problem. We have to answer this q queries. Q can be large. So let's try to make a very simple observation, and then this problem will become really easy. So let's call this area as the favorite area. So this area is the area where we want. So let's call this area Let's call this area as the good area. So this is the area where we want every star to be. So any star which is in the good area will not be moved, need not be moved, right? So if a star is already in the good area, then there is no reason we will move it, and any other star will have to be moved. So there is no way, for example, let's say there is a star here. So there is there is no way that we can make this work without moving this particular star, right? And this star will contribute exactly one operation, right? So now it makes our life really simple because we know exactly how many operations will be required. So the number of operations will be the number of stars which are not present in the good area. So because these are the only stars which will have to be moved, and since in one operation we can move a star anywhere in the grid, then it will contribute exactly one operation. So we will take a star which is in the bad area, and we will find any empty space in the good area and we will put it there. And once we are done with the algorithm, we will be sure that in the final grid every star will be in the good area. So the number of operations for that particular query is the number of stars which are not present in the good area. Now the only problem is, how do we actually compute this fast enough? Well, to be honest, there is a way to solve this problem in O of 1 time per query. There is also a way to solve this problem in log of nm time per query. But what we can notice here is that the values of n and m are both up to 1000 only, and q is up to 2 into 10 to the 5. So if we even take O of n time per query, it won't be that bad because it will be 2e8 operations, and the time limit is flexible enough to allow that. So what I'll describe now is, I'll describe a very simplistic solution which takes O of n time per query. So let's see how that solution is going to work. So what we'll do is, we will make use of 2D prefix sums. So we'll denote a star by a 1 and a dot by a 0, obviously. So what we'll maintain is, so for each column we will maintain prefix sums. Right? So basically for each column, like for example in an array we maintain prefix sums. So basically for each column we will maintain separate prefix sums. So what I'm trying to say here is that for the column j, prefix sum of ij is basically the sum of first I elements in the jth column. So this is what I'm going to maintain. Okay. Now what happens is that I know that I will also maintain the total count of all stars. So we'll maintain the total count of stars. So let's say this total count of stars is some variable tot. Okay. So if we have this variable tot, we know exactly how the final state of the grid is going to look like. A few of these columns will be completely filled, and this last filled column will have some of its prefix filled. So but how many of these columns will be completely filled? It's very easy to find out. So completely filled columns. So the first few columns will be completely filled, but which are going to be these columns? Well, the number of columns that are going to be completely filled is nothing but the quotient of tot divided by n, because in every column there are these n stars, and so the total number of completely filled columns will be tot by n, and the number of stars in the last column is going to be nothing but tot modulo n, right? I hope this is easy to understand. This is just basic mathematics. These tot by n columns will be completely filled, and in this last column there will be tot modulo n stars. Okay, right. So now what we can basically do here is, once we have these prefix sums with us, right? So what we can do is, we can iterate. So let's say this value is div and this value is rem. So what we can do is, we can first iterate. So for I from 1 to div, so we want to calculate the sum of these entire columns. Okay, So the sum in this entire, basically the idea here is I calculate the number of stars which are in this good region, and I already know the total number of stars. So the answer is going to be tot minus the number of stars in the good region. So I'll calculate the number of stars in the good region. So I will go from 1 to div and basically I will, let's say I have an answer variable, answer equals to 0, and I will add to my answer variable the prefix sum of the ith column and the nth element, that is the entire sum of the ith column. The entire sum of the ith column basically means the sum of its first n elements, so it will be prefix sum of ni, obviously. Okay, and then I also have this div plus 1th column, and the number of elements here is equal to rem, and so finally I will also add answer plus equals to prefix sum of the column that we are talking about is div plus 1, and the number of elements that we want is rem, and that's it. We have basically completed the entire sum, and then what we'll do is answer is equals to tot minus answer. Okay, so that's it. The only thing which I'm missing out here is that once I receive a query, I also have to change the state, right? So let's say in a query I get this particular cell, and I have to change the state of this cell. So I have to change the state of this cell. So then what happens is I have to erase the star from here and put a dot here, right? So then if this becomes a dot, then I also need to update my prefix sum array, right? So I will update my prefix sum array for this entire, for these many cells, and updating this is also will also take me O of n time, and this loop will also take me O of n time. So basically I have answered the entire query in O of n time, and to be precise I am taking 2n number of operations, and 2n operations means 2000 operations, and for 2 into 10 to the power 5 queries, that makes it 4e8 operations, which is still worth a shot in 3 seconds, and it turns out that it actually passes. So that's well and good. So yeah, that is it. Let's just have a look at the code. First of all, I am taking in my vector as input, and then I am first of all calculating these prefix sums array, and I am also calculating this tot variable. Then I take in the query. If the cell in the query already contains a star, I will decrement tot and make it 0. Otherwise, I will make it 1 and increment tot. And then I will update my prefix sum. It is very important to update this prefix sum for the yth row, for the yth column, right? And now I have div is equals to tot by n, rem is equals to tot modulo n, and basically we iterate from 1 to div and add p sum of ni to my answer. Then we add p sum of rem div plus 1 to the answer, and then answer will be equal to tot minus answer, and this basically works, right? So yeah, this completes the solution to problem F. Now let's come to the last problem that we'll be discussing today, problem G. This one is also a bit educational, so I really enjoyed this problem. For a lot of time I wasted a lot of time in reading these conditions wrongly. I read these signs to be greater than, less than, equal to instead of less than, and I was like really confused that if this is a less than equal to there, then why do we even need to remove some edges, right? So yeah, that was something I did wrong. I also wasted a lot of time in problem F because I thought that in one operation we can move a icon to any of its adjacent cells only, and that made the problem 10 times more difficult, so I wasn't able to solve it. But then I later realized that we can move it to anywhere. Anyways, so let's try to read problem G. So here we have a directed acyclic graph, and it consists of n vertices and m edges, vertices numbered from 1 to n. There are no multiple edges and self loops. So we have the in degree of, we have in of v as the in degree of v, out of v as the out degree of v, in dash v and out dash v as the in degree and out degree of v after we remove some edges. Basically we are asked to remove some edges, and we are asked to remove some edges in such a way that finally this condition is satisfied. And the condition is that the final in degree of every vertex should be less than its initial in degree, obviously if its initial in degree was positive. Similarly, the final out degree of every vertex should be strictly less than its initial out degree, given that its initial out degree was positive. Okay. And we can remove as many edges as we want. The only thing that matters is that these two conditions should be finally satisfied. Notice that it is strictly less than here, not less than equal to. Okay. Now Let's call a set of vertices S as cute if each pair of vertices U and V, such that both U and V belong to S. For each of these pairs, there exists a path either from V to U or from U to V, using the non-removed edges, obviously. So our goal is to find the maximum size of the set S that is possible after we remove edges, such that both in degrees and out degrees of the vertices either decrease or remain equal to 0. Okay, so that is the problem. It is a bit difficult to understand. It took me around 15 minutes to just understand the problem, but once I did it, things became really clear. So let's see what's going on here. So we have a directed acyclic graph. We have to remove some edges such that finally the in degree and out degree of each vertex, it either remains constant, either remains equal to 0, or it decreases. So it can't remain same. So the main thing to notice is that neither in degree nor out degree can remain the same if it was positive. Okay, and once we do that, we need to maximize the size of the cute set S. Okay, so let's try to see what we can do here. So obviously it is a directed acyclic graph, and in almost all the problems involving directed acyclic graphs, we have to look at the topological ordering of all the vertices of the graph. So it makes sense to look at the topological ordering of all the vertices. So let's say I have the topological ordering of all the vertices, and I look at that and play around with it. Okay, by topological ordering, what I mean is that for people who don't know what topological ordering is, then that is basically a prerequisite to solving this problem. So I recommend you to go to cpalgorithms.com and learn about it. There is a very nice article about it given there. So now I know that any edge which will be there in this graph will be from left to right. Okay, so any edge will be from left to right. So for now, let's forget about the condition that we have to remove certain edges. Let's only try to maximize the size of this cute set and see how this cute set will basically look like. So this cute set is a set such that any two vertices belonging to this set, there is either a path from one vertex to another or the other vertex to the other. Okay, but since all the edges in this topological ordering are from left to right, the path obviously is going to be from the left vertex to the right vertex. So let's say we choose some of these vertices and claim them to be a part of our cute set S. Let's say this is our cute set S. Okay, now I will write down a very important claim and then prove it. So the claim is this cute set S is going to be nothing but a simple path in this graph. But a simple path in this graph. And the proof again is really simple here. So the proof is, if we look at any two consecutive vertices in our cute set, so now let's try to look at any two consecutive vertices in the cute set. Obviously by consecutive I mean two vertices which occur one after the other in the topological ordering and are in the cute set. For example, we can look at these two vertices. Let's look at these two vertices. So what happens here is that between these two vertices, I want them to be connected to each other, obviously. So I want this left vertex to have a path to the right vertex. Okay, and the only way these two can be connected, the only way these two can be connected is if there is a direct edge from, let's say the left one is U and the right one is V. So let's say this is U and this is V. So the only way that U and V can be connected is if there is a direct edge from U to V. The reason for that is, let's say that there is no direct edge from u to v, and there is an edge from u to something which is to the right of v. Let's say here, right? So if there is no direct edge from u to v, and there is an edge from u to the right of v, then obviously we cannot come back to v from here, right? Because every edge is from left to right. There is no edge from right to left, so we cannot come back from u to v. Okay, and let's say there is an edge from u to some vertex here, then there is no and then there is an edge from this vertex to this vertex here. Then there is no reason that we are not including this particular vertex in our cute set S, right? If this is the situation, then there is no reason this vertex is not in our cute set, because we want the maximal set. So for the set to be maximal, we have made sure that between any two consecutive vertices which are in the cute set, there has to be an edge between these two vertices, and that basically proves that this cute set is nothing but a path in the directed acyclic graph. And so the problem boils down to finding the length of the longest path in a DAG. Obviously right now I am ignoring the situation about removing the edges. So now we need to find the length of the longest path in a DAG, and that is a very, very standard problem. It can be solved using a conventional DP. So if I am explaining this solution, then I am assuming that you already know how to solve this problem. It is a very conventional DP, where DP of I is basically the length of the longest path which ends at the ith vertex, and then we look at all the edges which are incident to the ith vertex. Let's say there is an edge from u to v, then we say that dp of v is maximum of dp of v and 1 plus dp of u. So the way to do that is for all edges u to v, we do dp of v is equals to max of dp of v 1 plus dp of u. So this is a very easy problem, but right now we are ignoring the condition that the in degree and out degree of every vertex must decrease. So how do we handle that situation? So then what we'll do is, once we have the topological sort and we are doing a DP, obviously the basic pipeline remains the same. We will have dp of v. So dp of I is equals to length of longest path ending at node I. Okay, so now we are obviously going in the topological order. So what we'll do is, if we want to calculate dp of I, we will look at all nodes in the reversed adjacency list of node I. By reverse adjacency list, all I mean is that I'm looking at all the edges which are incident to I. Okay, so let's say there is an element j and there is an edge from j to I, and I'm looking at the element j. I want to use the value of dp of j to update the value of dp of I. Okay. So there are two possibilities. One possibility is that the only edge, so case 1, only edge going out of j is the one from j to I. Okay, if this is the case, then we can't really consider this edge, because we have to remove this edge, right? Because the out degree of this j has to be decreased by 1, and since this is the only edge which is going out, we have to remove this edge. So we have to remove this edge. So we can't consider this, right? We cannot consider this edge. Otherwise, let's create a vector. So we have a vector with us, and if this is not the case, otherwise, so let's write an if condition, something like this. So otherwise what we'll do is, we'll push the dp value of j into our vector. We'll do something like vector dot pushback dp of j. So we will do this for all the j's which are in the reversed adjacency list of I. Okay, and we will also create a boolean variable. Let's say we have a boolean variable found, and if this is the condition that the only edge going from j to I is the one which is contributing to the out degree of j, then we will make this boolean variable found to be equal to true. And what this denotes is that we have already removed an edge from the in degree of I. Remember, we also have to reduce the in degree of I. Okay, so finally, after looking at all the elements from the adjacency list of j, what we'll do is, first we'll check if we have found, right? So if we have already found, That means if the value of found variable is true, that means we have already removed an edge which was incident to I, and now we don't need to remove any other edges because we have already decreased the n degree of I. So if we had found, we just let's say x is equals to maximum element. So let's say mx is equals to max element in the vector. Then dp of I is going to be 1 plus mx. Okay. But if we have not found, then what we have to do is we will check if the size of this vector is equal to 1 or not. So if size of vector is equal to 1, size of vector is equal to 1 means that we have only one viable edge with us. But the thing which we are forgetting here is that we have to remove one edge because we haven't found anything yet, right? So we can't take this edge. So then dp of I will be equal to 1 only, which is just the ith element. Otherwise, if the size is greater than 1, then we can simply take the maximum element, because we don't care which edge we will remove. We will remove some edge which is not giving us the maximum value, and hence we can say that dp of I is equals to 1 plus mx. So these are all the cases that you have to take into consideration, and then you can easily solve this problem. If the casework here is not clear to you, I think just think about it a bit more and it will start making sense to you. The main goal here is to decrease the in degree of all the nodes as well as the out degree of all the nodes. That is why we have to keep this found variable. If we have already removed an edge which was incident on I, that means we have already decreased the in degree of I, so we can just simply take the maximum element. Otherwise, we have to remove one element, right? So if the size itself is 1, then we can't take that particular edge. Otherwise, we will remove a smaller edge and we will take the value 1 plus mx. And finally, we will look at all the dp values and take the maximum of them, and that is going to be our answer. Okay. So yeah, this completes the solution to problem G. Let's just have a look at the code. So what I'm doing here, first of all, is I'm taking the input of my graph and computing the adjacency, reverse adjacency lists. Then I'm using the standard Kern's algorithm for finding out the topological sort of the graph using a queue. This is a BFS-like algorithm, as you can say. Then I am doing a DP, and then I am doing all this casework. I am going in the reverse adjacency list. If size of that is equal to 1, then I am doing found is equals to true. Otherwise, I am pushing the DP value in my vector. Then I sort the vector. If found is true, then I just check if the vector contains an element and I'll take the maximum element. Otherwise, if the size of vector is less than equal to 1, I don't do anything, and else I will take the maximum element again. And so I have the dp value of my current element in the topological order, and I will maximize my answer with that. Okay. So yeah, this completes the solution to problem G as well. These are all the problems that I had in mind. So thank you so much for watching, and I will see you in the next one.